Okay, so good morning, everyone. I'm really glad, Dr. Bastos, that you accept our invitation to speaking to us. You are our first speaker this year, so we are really happy to have you here. So just to explain a little bit what you are. So basically, we are the ACS Grad Student Committee. What means that we represent all the grad students population of the American Society of Agronomy, Crop Science Society of America, Soil Science Society of America. So our main goal is basically bring hot topics for all the grad students, and that can help through the grad school, can anything. And also, if you guys are here and you, for example, our goal is have different meetings, webinars through the whole year. So we have any topic in mind that you want to share and you want to email us about it. We are really happy to see if we can get someone to speak about it. And we're going to be announcing soon the next webinars. Our next webinar will be around June, and then we're going to have July and another in August. So we are going to have few webinars during this year, but I'm really happy about it. And yeah, and that's it. And again, thank you so much, Dr. Bastos, to be speaking with us today. We are really glad that you were able to do that to us, and all the community appreciate it. So with that, I'm sure you want to talk a little bit, introduce Dr. Bastos, please.
Good morning, everyone. I'm Amrinder. I am Dr. Bastos, like a PhD student, so I will give a little bit just description or brief bio. So like Dr. Bastos, he's like assistant professor in integrative precision agriculture at University of Georgia, Athens. So his research focuses on using of a proximal and remote sensing geospatial, soil, and temporal weather data to inform crop management practices from within field to a regional scale, with a focus on nitrogen management and crop quality mapping. He also teaches on the topics of precision agriculture, digital agriculture, and statistical programming and data science applied to the agriculture. He's a very good teacher. He's like a fabulous teacher and mentor too. And his all the lectures are on YouTube. So if you like his today's lecture, you can see here more videos on the YouTube. We can share the link later on that too. Yeah, thank you, Dr. So you can carry on.
All right, thanks, Jessica. Thanks, Arminder. So I guess, I want to share a few thoughts before we get started. So first off, wanted to thank the ACS Grad Student Committee for inviting me. I know that there's many great topics that students are interested in learning, and stats and programming is one of them. So I appreciate the invitation to be here sharing with you all some thoughts around those two topics. Just a quick agenda. So we're going to be going for at least the schedule. We have 1 hour, so we have until 11 a.m. Eastern time, at least on my side. I anticipate we're going to go over a little bit on time. If you can stay for that you're welcome to stay. If you have to leave, this is being recorded. So I'm going to post the recording along with the code that you already have, share with you. So later on you can catch up if you need to, or if you just want to revisit the notes and the lecture notes. I do want to start sharing my screen here just so you see what I'm seeing as well. So let me go ahead and do that. Can you all see my screen?
Yeah. Yes, we can see your screen.
So I just want to first off start here with the link that if you sign up for this workshop, you receive these instructions already, where I share with you the link to my GitHub repo. So this is where you're going to have the code, the complete code for what we're going to be doing today. And also in there, I had some instructions for you if you wanted to, download the code, download the data, have the files on your side so you can code along. Also there are a couple important links. So one of them is the link for the slide deck. So that we're going to first go through some slide notes here for us to set the stage as far as the topic that we're going to be covering in code later. So here's the link for the slides and that you can use to follow on your side. I do want to quickly share the link to this GitHub repo on the chat. So in case you did not have a chance, let's see here, where's my, there we go. If you didn't have a chance to, hold on. All right. Okay, so here's a link for this GitHub repo, which has further links for the slide, and also the code is in this repo itself. So if you didn't have time to do this beforehand, I don't think you're going to have time to do that now. Today, we're basically going to be covering 1 hour, what I normally cover in about 10. So it's going to be really fast, and it's just going to be, some concepts and then providing you with the code to run one example. That's my goal here. If you're not familiar with R, if you're not familiar with what we're talking about, I don't expect you to get out of this workshop being an expert. You're just going to get some introduction to it, some code to play along on your side. That's my goal for today. All right, so I'm going to go ahead and follow the slide deck link here. So I'm just going to launch that. This is an active link. You can follow these slides on your side as well if you wish. And if you wish just to follow along with me, you're also welcome to do that. All right, so our goal today is going to be to talk about designing and analyzing ag studies, an intro and R example. So we're going to go through these slides first, and then after that, we'll switch into the programming side of it, where we're going to actually be developing the code and going through each step of that analysis. So we're starting here. The goal of this presentation is going to be to explore some concepts in experimentation. So first, the planning, an experimentation planning workflow, hypothesis setting, a study design. So talking about both treatment and experimental design. This sometimes is a confusion that we have, where it's not very clear what is one, what is the other, what is the purpose of each one of these components of design. So we're going to be talking about that. Briefly, we're going to touch base on the differences between a CRD, which is a completely randomized design. It is the simplest design that we find in agriculture. Comparing that with RCBD, Randomized Complete Block Design, which is one of the most popular designs that you see in ag. I'll share with you some resources afterwards in case you wanted to keep learning, at least using my material. And then we get into the R code part of the workshop. All right. So overall, I like seeing this figure here and just setting up what is this workflow that we're looking for when we're defining a study and conducting a study. So really, if we start here on this left side, it all starts with some question, right? So curiosity, you have a question about something, either because you observed, or maybe you read on the literature, or you have an idea. It always stems from curiosity, which based on that, we define our hypothesis, right? So you define, well, I hypothesize that maybe doing this to my crop, my plants is going to have this impact on yield, on some type of loss, on some measure that we're measuring at the end. Based on our hypothesis, we determine our objectives, and our objectives are directly linked with the treatment design. So this is what I want you to keep in mind. Treatment design is a component of your design that addresses your objectives. On the other side of this, we have the experimental design. So the experimental design is going to be the part of your study design that's going to be related to experimental units and how much of that you have available to conduct your study, and also the homogeneity or lack of homogeneity of that experimental material. So experimental design component of your study design is going to address experimental unit quantity and also homogeneity or lack of it. So treatment design connected to your objectives, experimental design connected to the material you have to do that study, how much of it you have, and how homogeneous or not that is. So I want to set up this working example here because we're going to be talking about this in the slides and also when we get to the coding part. So let's say we have a fertilizer rate study where I want to conduct a study to assess the effect of nitrogen and potassium fertilizer rates on crop yield. right? So one way to define our hypothesis here, which always think of your studies need to be hypothesis driven. You have to come in with a hypothesis that then you collect data to test the hypothesis, right? So we always need to have a starting hypothesis. So maybe here we could hypothesize that as I increase nitrogen and potassium fertilizer rates, that will increase crop yield as well. This is a very simple hypothesis. I am making a statement. Notice how I'm not saying that I hypothesize that increasing nitrogen and potassium may increase crop yield. I'm not putting a word here that make my hypothesis weak. I'm making a statement. I'm saying this is what I think is going to happen. This is my hypothesis coming in. Let's do this study, collect data, and test to see if this is true. Even if at the end you collect data that says your hypothesis was not correct, that's okay, right? That's part of science. But we need to come in with a very strong, bold hypothesis that can be tested. So from this hypothesis, then we can come up with some objectives, right? So maybe the objective here would be to assess the effect of different nitrogen and potassium fertilizer rates on crop grain yield. See how they're very much linked. So one is making a statement, the other one is just defining that that is your objective, but they should be linked. Now, we just talked about the study design being composed of your treatment design and your experimental design. Right, so those two pieces of your design make your study design as one thing that you can think of two pieces: treatment design, experimental design. So let's talk a little bit about treatment design first. So treatment design is the part of the study that will be related to what treatments you need to answer your hypothesis and objectives and how they're related to one another. So here, the goal of the treatment design. So, if you just focus on this, like you have your objective, the goal of your treatment design is to select treatment factors and levels that once you collect data from them, you would be able to answer your objective. So in our case here, we have, if my objective is to assess the effect of potassium and nitrogen rates on crop yield, I have to have at least a few levels of those treatment factors so I can assess their effect, right? If I just have one level of potassium, one level of nitrogen, I really don't have enough treatments to tell me the overall effect. I just know one level. I don't know how yield would change if I have higher levels or lower levels, right? So let's pick a few levels for each of these fertilizer sources or nutrients of nitrogen and potassium. I'm just proposing here that for nitrogen, we do 3 rates: 0, 100, and 200 kilograms of nitrogen per hectare. And potassium, also do 3 rates, so 0, 30, 60 kilograms of potassium per hectare. Now, if I'm also interested in the interaction of those two factors, so not just nitrogen by itself, not just potassium by itself, but the interacting effects of both, we need to have in our treatment design all the combinations between my nitrogen rates and my potassium rates. In this case, because I did propose that we had 3 levels of nitrogen and 3 levels of potassium. If we do a full factorial, this would mean that we have 9 total treatment combinations, right? Which is every single 3 of the nitrogen rates by every single 3 of the potassium rates in all possible combinations across them. So in total, in this study here, we would have 9 total treatment combinations. In other words, I need to have all those 9 treatments and those combinations so I can find the joint optimum nitrogen and potassium fertilizer rates that will optimize crop yield. A way to refer to this, and the way that you would write on your papers, in your presentations, the way that you would find this in the literature, is that this can be called a cross 2A factorial treatment design. Remember, we're talking about treatment design. We have not said anything about experimental design yet. So this is a cross 2A factorial treatment design, or perhaps you can also say it's a cross 3N rate by 3 potassium rate treatment design. This is how you could describe it as when you write about this type of design. Now, this basically determine our treatment design. And notice that selecting 3 rates of nitrogen, 3 rates of potassium, doing all the interactions or all the possible combinations of those 3 rates of each nutrient has set the treatments that we can use to collect data and then answer our objective of assess the effect of potassium nitrogen rates on crop yield. So we have not talked about experimental design yet. So let's think about that. What is the use of experimental design and how can we determine what we need? Experimental design, so the second component of your study design. So remember, study design is treatment design plus experimental design. We just talked about treatment design. Now let's focus on experimental design. This component of the design is related to how your treatments are assigned to the experimental units. And the decision of which experimental design you're going to need is going to be guided by two main factors. One of them is the homogeneity of your experimental material. The second one is limitations, such as funds, space in an incubator, size of benches, size of a field, or really any other limitation that you may have that impacts how much material you have to conduct that study. Our goal here is going to be to select the simplest experimental design that will accommodate all of our treatments and their replications in homogeneous experimental units. This is a key word. We're trying to make sure that our study is the most homogeneous possible, so we have the most chance of finding statistical differences across our treatments. So this is the part that experimental design is going to help us to address. Now, we've been talking about experimental design and experimental units, and this is a very key concept in experimental design. So experimental unit is going to be the smallest unit in an experiment that is randomly and independently assigned to a treatment. And if you think of like plot research, this is normally your plot level, right? So you randomize your treatments in a way that each plot is going to receive one treatment. So let's say maybe what we're seeing here in this picture, it may be something that you've seen across your experiences as well. You can see the two flags there delimiting a plot, and then I'm applying a given rate of nitrogen to that plot, right? So this would be one plot that's receiving one nitrogen rate. And this is the unit of true replication. This is very key as well to understand, especially when we're defining subsampling or true replication in a design. A couple more concepts here. So replicate would be different experimental units. Remember, experimental unit was the smallest unit on the study receiving a randomized treatment. So a replicate would be different experimental units that receive the same treatment. And replicates would exist in most designs, including the ones we're going to be talking about here. A block is a little bit of a different concept. So it's going to be a set of experimental units that are grouped into homogeneous condition. So a block would be a homogeneous condition. We're going to see an example of this to clarify what I mean by that. But within a block, you're going to have many plots where at least for the design that we're going to be talking about today, you should have at least one treatment appearing, should have each treatment appearing at least once in a block for that to be a complete block. And your treatments are going to be randomized within each one of the blocks. So if you have 4 blocks, you're going to have 4 randomizations, 1 for each of the blocks. So this is just to kind of illustrate that. So here I'm showing you basically 2 blocks. So block 1 is the one that has a lot of annotations, and the block next to it, the column next to it is block 2. If we just focus here on block 1, in our case, if you remember, we have 9 treatments, right? So 3 nitrogen rates by 3 potassium rates, that gives us a total of 9 potential treatment combinations. So we have 9 treatments, and we see the numbers here representing each one of those treatments. So we see that within block 1, we have all treatments being randomized here. So block 1 is the red rectangle. A plot or experimental unit is this beige rectangle here. So this would be a plot. And the plants inside of the plot would be our observational unit. So even though I'm applying my treatment to the whole plot, so I'm applying fertilizer rates on the whole plot, if at the end you come and you maybe harvest 6 plants, or how many plants you're harvesting from this plot, though the plants are your actual observational units. So experimental unit is where you apply your treatments. Observational unit is where you collect the data that you're actually analyzing afterwards. So let's say if it's yield, or maybe if it's crop height, or whatever it is, right? That is your observational unit. In this case here, if we come back at the end and collect 6 plants for yield, my observational unit is 6 plants, but my experimental unit was the whole plot that received a given set of treatments. All right, so if we continue with our example of nitrogen and potassium levels, and we assume that we want to have 4 replications. So that's going to bring us to needing a total of 9 treatments times 4 replications equals 36 experimental units. So I need to have, in this example here, I need to have on my farm, my experimental farm, or maybe an on-farm study, space for 36 experimental units. At that point, so now I know how many treatments I have, how many reps I want to have, and how many experimental units in total I need for this study. Then you should ask yourself the following question. Do I have enough homogeneous experimental material to accommodate all those 36 experimental units? Before we answer that question, I just want to touch base quickly here on the 2 designs we're going to be quickly overseeing on these slides. So the first one, again, is completely randomized design. That's the simplest design, a very popular design, perhaps not the most popular, but a very popular design if your experimental material is homogeneous. We also have a randomized complete block design, RCBD for short. So these names are very similar and it's easy to get confused, but notice that CRD is going to be our simplest design. RCBD, so randomized complete block design, it's going to be a little bit more complex to help us accommodate lack of experimental material homogeneity, and is really one of the most popular designs you see in ag. So that's why we're going to be focusing on that more. So we have these 2 designs. If you ask yourself, do I have enough homogeneous experimental material to accommodate all 36 plots? If your answer is yes, then you can use a completely randomized design as the experimental design here. And then the treatments will be randomized to the whole area without restriction, meaning that you're going to have 36 plots, and it could very easily happen that one plot receives, let's say, treatment 1, and the plot right next to it also receives treatment 1, because you have no restriction randomization. Because again, you're assuming your area, your experimental material is homogeneous. So it should not matter if by random chance, a same treatment has 2 neighboring plots. It should not matter if your material is homogeneous. However, if your answer to this question here is no, I do not have enough experimental material to fit 36 experimental units, then you should consider what type of limitation you have and which design can help you to accommodate that variability. So let's say, for example, that in our example here, we say, no, I do not have a farm, a field in the research farm that I can accommodate 36 plots in homogeneous material. So we're going to have to know what is the cause of that lack of homogeneity. In our case here, I'm just give an example of soil texture. So let's say you go to the field and you see that you have 2 different soil types within the area that you were allocated. And you know that those 2 different soil types are going to impact the effect that your treatments have on yield. So you do have the heterogeneity in soil type in this case, and we know that heterogeneity will impact yield. We have to account for that in our design. So when we do have the heterogeneity, randomized complete block design can help us to accommodate that heterogeneity in your experimental material in a way that we can trust our results, even though we have that extra variability in the field. So we can accommodate this by choosing an appropriate experimental design. For that, RCBD could be one of them. It's going to be the one that I'm going to show you, where our blocks will be entirely confined within a given soil texture class. And you're going to see a picture of that here in a second to help you visualize what this means. And again, just a reminder, with randomized complete block design, each treatment, so we have 9 treatments in this example, each treatment will appear once per block, and every block is going to have every treatment. And each one of the blocks are going to have the 9 treatments randomized separately. So I do the randomization first for block 1, and then after that for block 2, and then block 3, and then block 4, in a way that I have restriction in my randomization. That was not the case with a completely randomized design. If you remember, I told you with a CRD, it could happen that 2 treatments could fall in the same column, if we think of a column being a block. Now with RCBD, I'm not gonna have the same treatment appear more than once in a block. Each treatment would appear one time in each one of the blocks. So here's my example for us. So let's say this is our field. Each column here is a block. I have 9 plots in each block because I have 9 treatments. And I can see that the difference in the background color. I'm just showing you here an example of different soil types in your area, right? So let's say on the left side here, we have a darker soil type. So maybe it's a finer texture that has better, nutrient and water holding capacity, is more productive overall. On the right side, I have a lighter color soil. So maybe a sandier soil that has lower water and nutrient holding capacity, maybe a lower yield potential overall. Notice that on an RCBD, I have my blocks completely confined in each one of those sources of variability. In our case, soil variability, right? And notice as well that in each one of the blocks, I have each treatment appearing only once. I am highlighting here treatment number 1, just so we can look across it. You see that, this happens for all treatments, but if you just look at treatment number 1, it is appearing one time in each one of the blocks. And there's no block that has treatment number 1 more than once. There is no block that does not have treatment number 1. Every single treatment appears once in every single block. So this increased variability in crop yield that may be caused by soil texture, that effect will be confined to the block effect, and it's not going to interfere with our assessment of treatment effects. And because of that, because this extra variability of soil, in this case soil texture, is confined to the block effect, it can be properly removed. We can properly dissect that noise out of our treatment effects and still be able to make to the most extent possible, accurate and precise, unbiased comparisons of our treatment means. Even though we have this variability in the field, but we use a design that allowed us to dissect that variability out and still be able to make good inference on our treatments. So a very quick summary of these slides here is that treatment design, again, addresses the research question. So treatment design has nothing to do with experimental design, experimental material heterogeneity. It's just addressing, treatment design is just addressing what we need to know and to do to answer your research questions. That's the goal. Your experimental design is the part of your design that will address the lack of homogeneity and or limitations of experimental material. So if I tell you, again, in our example here, our treatment design was a 3 nitrogen by 3 potassium factorial. Our experimental design was a randomized complete block design. Those 2 pieces of information you need to describe in your material methods, but they're separate, right? So they're part of the same study design, but they're addressing different components of it. One, treatment design addressing directly your objectives. The other, experimental design, is addressing the homogeneity or lack of it of your experimental material. And together they make up your study design, which is important for when you're planning, but also when you're analyzing your data. Because the design that you plan and that you implement in the field has a model behind it. And when you come back with the data that you collect and you want to analyze the data, you should know what was the design, how the design translates into a model, and how the model translates into code to make sure you are analyzing your data correctly. Because software, regardless of what it is, it could be Excel, SAS, R, whatever it is, software is not going to tell you that you're doing the wrong thing. If you go on the field and you run a randomized complete block design and you come to your computer afterwards, you get the data, and you misspecify your model as a completely randomized design, R is not going to yell at you. It's going to go through. So that's going to be on us as the researchers to make sure that first we plan our designs properly with a design with an overall study design that answers objectives and also addresses potential lack of experimental material homogeneity, but also that afterwards you come to your software and you properly specify that model that represents what you did on the field, so you can have good inference on your data. And again, by choosing the correct experimental design, especially, is going to allow for you to be able to do unbiased and accurate treatment comparisons. If in that example that I just gave you of the two different soil types, if we run a completely randomized design there, our errors around our means are going to be very much inflated because they're going to have that extra effect of soil variability. And because we didn't block, if we use a CRD, then that soil variability, there's no way you can separate that from a treatment because you don't have the block information there. It's just a treatment. So by using and choosing the appropriate design for that situation, in this case on RCBD, a randomized complete block design, we can dissect that extra variability coming from soil, leaving our treatment comparisons still unbiased and accurate to the most extent possible. I have some resources I want to share with you before we get to the coding part. So I teach a couple of courses here at the University of Georgia. One of them is Data Science Applied to Ag. This is a hyperlink. If you click on this, it's going to take you to my website. So as Amrinder was saying earlier, I have a full schedule here where I have different slides. I have different scripts that are on GitHub. I have the recordings of all my lectures on YouTube, and I have some reading materials if you want to assess. So again, today is very compressed. We're doing this very quick and just touch basing on some of these concepts that I normally teach in at least maybe 6 to 7 hours. We're doing it in one. So if you want to explore more, you can use these as resources. I have a lot of lectures, a lot of videos, and the codes are going to be on the GitHub repo of the class. So you can go and learn on yourself if you want to. So in this class here, I have 28 videos, 17 R scripts, and 12 slide decks that include topics from Intro to R, how to plan, design, and analyze a completely randomized design, randomized complete block design, a split plot design, repeated measures. Also have lectures on how to get Git and GitHub working and setting up and working on your computers, how to find open source data, how to run different types of multivariate models, and machine learning topics. So you can explore that on your own later if you wish. That's one resource that I have to share with you. Now let's get into the coding part of this exercise. So we're going to be analyzing this example that we were talking about in this lecture. So we're going to be analyzing a 3 nitrogen rates by 3 potassium rates in a randomized complete block design with blocks treated as random effects that assess the effect of those fertilizer rates on crop yield. So at this point, what I want to ask you to do is, let me minimize here. So this is the folder that if you follow the instructions on GitHub, you would have this folder here in your computer, where we have a code folder, a data folder, output, and then we have some extra files there. I want to ask you to just go ahead and click on the code folder and click on this QMD file there. So the 2024 ACS workshop, RCBD bastos.qmd. Let's see, we have a question here. Could you please share the link of your course in the chat? Yeah, so Abdullah, if you use the link here that I shared for the GitHub repo, on that GitHub repo, we have a link for the slides, and on the slides, you have a link for my course. So you can go through that route as well to get there. So that link is in the presentation. All right.
We have another question, Dr. Bastos, before you move forward to the coding part.
Yes.
So it's related to your experimental design that you had on your slide. So your 4 replicates, you divided them into 2 different soil type blocks, basically. So each soil type will have 2 replicates for each treatment, right?
Yes.
So are those two treatments enough to explain the variability within the same soil type, maybe due to experimental errors or like environmental factors, or maybe just human errors?
So that is a question. It's a great question. It will depend a lot on many factors, right? So for example, if we are hypothesizing that different soil texture classes will impact yield and will interfere with your treatments, right? So let's say, for example, if this ends up not being a block design, so let's say if we just do a completely randomized design that has no limitation in randomization, right? So if it happens that the same treatment by random chance happens to appear only in one soil type and not in the other, then that treatment mean is going to be biased, right? So let's say treatment number one, whatever that would be, if I use a CRD and it falls all on the dark soil that we are hypothesizing has higher yield potential, that treatment one may have higher yield than other treatments, not because of the treatment itself, but because of the soil effect, right? So with a completely randomized design, we cannot separate this effect of treatment and variability of soil in this case. With the randomized complete block design, if we plan ahead, we can, right? So even though there will be this noise coming from soil variability, we can separate that from the treatment effects. Now, then the question becomes how strong, first, how much is that variability of soil variability, right? And especially how does that compare to your treatment? So the magnitude of the effect of a treatment, right? So let's say I know nitrogen affects corn yield, but I have my treatments and let's say I'm just getting started in this field and I select rates that are like 0, 10, and 20 pounds of nitrogen per acre. I have treatments there. There are 3 levels, but most likely the difference in yield between 0, 10, and 20 pounds of nitrogen per acre is not going to be large enough for me to really see an effect, at least not with four blocks, right? So it will depend also on the strength of the effect of a treatment. So if I come here and I know that nitrogen has an effect, but I should have a wider range of rates to be able to see that effect come through. Instead of using 0, 10, 20, I use 0, 50, 100. That will be easier to find as an effect from nitrogen itself, right? So it's going to be related to that and also to how much extra noise you have here. Because a lot of times, maybe you don't even know you have soil variability in your field if you don't sample and you just do a CRD without knowing. So that's going to be adding extra noise to your treatment effects as well. So the smaller is the treatment effect as far as like how much of yield impact you are expecting to see, then it's going to be harder to find it. So I guess this gets into the conversation of statistical power, which is going to be affected again by the magnitude of your treatment effect, by how much variability you have there, and what level of treatment differences you're expecting to find. And that's a whole lecture on itself. But so here again, the goal is not necessarily for us to have like a good amount of replication to be able to separate the effect of soil. As long as we do a design that we properly have our blocks placed in a way that they are confined within homogeneous material, a block is totally within homogeneous material, we can separate that effect. That's really the goal. And then the extra question of, well, is 4 reps enough for that? Should we have 10? Could we get by with 2? Then that's more of a statistical power conversation that goes deeper than this.
That makes sense. Thank you so much.
Awesome. Thanks for the question. All right. So getting back to our code here. So if you double click on this QMD file, this is a Quarto file. It should open an RStudio window on your side. So this is what I'm seeing on mine. So again, this is not an intro to our class. So if you're looking at this right now and you have no clue what's going on, then I would say just watch along. Don't worry too much about it. You can follow my intro to R videos later if you want to learn more. But if you are familiar with R, if you already know how to use R Markdown files, this is a Quarto file. It's very similar to R Markdown, where I have some text. I'm going to have some chunks, which is where, so this would be a chunk, is where the actual code is happening. And then we're just mixing in the same script here, narrative, code, and outputs. So we're just going to go through this code here. I'm going to tell you what's going on and how we're going to be using this script here to run a randomized complete block design analysis with the data that we just talked about in the lecture. All right, so if you're able to launch this on your site, if you follow the instructions before the workshop, you should be able to code along with me, and you should be able to run the chunks that they should work. If you were not able to do that catch up before the workshop, or if you don't have enough R experience to get to this point, you can just watch along, and I'm sure you're going to be able to get some very important takeaways as well just by watching. All right, so a few points here is you can use this outline here on the right to navigate the script. This has a lot of sections that do different things in this script, so you can use that to navigate. Again, this is not an intro to our workshop. I am assuming that for you to be able to make sense of everything we're doing on the code side, I am expecting for you to be familiar with R Studio, Quarto scripts, chunks, data wrangling with dplyr inside R, and plotting with ggplot2. If you're not familiar to most of these topics, you may not be able to follow, and that's follow on the code side, and that's completely okay. You can revisit this later if you need to, and you can use my other resources to learn how to catch up and get to this point as well. All right, so a quick intro here. So my goal of this script is to create an analytical workflow for a randomized complete block design with random blocks that starts at importing data and goes through a lot of the steps and until we get to publication ready plots. That's my goal. So we're going to bring in data, wrangle, explore the data, run a model, check a whole bunch of things, and then produce a plot in the end. Just to remind you, so the objectives of this study is to assess the effect of different nitrogen and potassium fertilizer rates on crop grain yield. The treatment design is a 3 nitrogen rate by 3 potassium rate factorial. The experimental design is going to be a randomized complete block design with 4 blocks. These were already determined even before this study was established on the field. I'm just reminding you because that's going to be important for us to know when we create the model to analyze this data. All right, so if you did the work before, if you follow the instructions before starting the workshop, you should have installed this package, Easy Packages, and then you can load it, and then you can use the function packages where we're calling each one of the packages we're going to be using. So if you just go ahead and run this chunk, you should just go through it, and hopefully if you are already installed all the packages, you're not going to have to install now. It's just going to load the packages. That's my goal for you to be able to follow along. Now we're going to import this data, and just to let you know, in my classes, when I have a lot more time, I do a lot more live coding with my students. In this case, we don't have that time. So I already left you maybe 99% of the code here. And I just want to tell you what this is doing on each step. So here we're going to import our data. This data set is in the folder that is called data. So if you go here on your files, the script is in the code folder. There is a data folder as well, whereas this data set is a CSV data set. We're going to use this function read CSV because it is a CSV file to read in this file into our environment. So once I run this line of code, it reads the data, assigns that to this object, and I'm just going to print this object below. So we see it has 36 rows. If you remember, we had 36 experimental units because we had 3 nitrogen rates, 3 potassium rates for a total of 9 treatments, and we repeated them 4 times. So we have 4 blocks. So we have 36 observations here in 5 columns. So we have a wrap column, a nitrogen rate, potassium rate, and then yield. So these are the data we're going to need to analyze this data. using our design model. So we're imported data. Now let's do a quick exploratory data analysis using some tables. So here I'm using the function summary. If we just run that chunk, it's going to print right below it. So for the columns here that are interpreted as numerical, we get a statistical summary that gives a minimum, quantile, median, mean, third quantile, maximum. So we see here that are basically interpreted all of our columns as numerical. And it gives, and really the only one that really is important numerically here for us to look at this statistical summary is yield. So we see here that the minimum yield here was 812 kilograms per hectare. The maximum was above 7,000. So that this is our distribution of yield as a quick statistical summary. I also like to check use this function glimpse to check variable classes. So you see here, we have our 5 columns. They're all being interpreted as integer, so as numerical by R. We're gonna have to change that before we run our model. So for example, even though my blocks are 1, 2, 3, 4, but it does not mean that block 2 is 2 times more than block 1, or that block 4 is 4 times more than block 1, right? That number there should not be interpreted as a numerical variable by the model. Because really, I could have named my blocks A, B, C, D, and they would have the same meaning, right? The numbers there is just to make it easy for us when we're planning, but they don't really mean much when it comes to analysis. So we're gonna have to treat our block and also our treatment factors. So treatment factors, nitrogen rate and potassium rate, right now are also being interpreted as integer, as numerical. We're gonna have to force all these to be interpreted as categorical before we run the model. That's what I'm doing here in this next part of the chunk. I'm starting with the data that we just imported above, and then I am I'm forcing rep and rate and potassium rate to be treated as a factor or as a categorical variable. So just go ahead and run the chunk, and then I'm assigning the result of that to this object RCBD DFW. So now we see rep and rate and potassium rate being interpreted as factor or categorical, which is what we need when we run analysis of variance. Again, if I come and use now the summary function on this new wrangle data set, I see that I still get the statistical summary for yield, but now for rep and rate and potassium rate, because now they're being seen as categorical. It just tells me how many rows I have for each one of the levels. So just wanted to show you that. All right, so we did EDA, exploratory data analysis, using tables above. I also want to make some plots. It's really, really important for you to visualize your data before you start running models, so you can catch, first, maybe you can create some hypotheses of what's going on, but also catch if you had any data entry errors or anything like that. So for example, if we were to have our yield here with the minimum value being a negative value, that's biologically impossible, right? There's no negative yield that you can measure in the field. So that would tell you there's probably something wrong with data entry, or maybe data curation, or maybe the machine that was harvesting had something going on with it and recorded the data in the wrong way. So it's always important to check your data, like we're doing with both tables and now plots, to make sure your data is accurate and it is what it should be. So I'm just going to run this chunk here. What I'm doing is just creating a box plot where on the x-axis, I'm putting the nitrogen rate treatments of 0, 100, and 200 kilograms of nitrogen per hectare. On the y-axis, I have yield, and then just putting some box plots with the points behind them, so we can create this understanding here. So we see, overall the box plot, the line in this solid line in the middle of the box plot is the median value. So we see here that it looks like there is a positive effect of yield as you increase nitrogen rate on this trial. I want to do the same with potassium. So the only thing I'm changing is on the x-axis now is potassium rate instead of nitrogen. We see that there's also a effect to potassium, perhaps even a little bit stronger than what we saw on nitrogen. So just creating this understanding and this visual hypothesis of what is going on with the data that you collected. Now we can also do a different type of plot again, I'm not spending a lot of time on explaining to you what the code is doing. You can do that on your own as you learn. But we're just now putting nitrogen rate on the x-axis, and then each plot here is a different potassium rate. So we can look into the potential interaction. It seems like for all potassium rates, as we increase nitrogen, we increase yield until a point, and then the lowest potassium rate had the lowest increase in yield as you increase nitrogen. And when you apply the intermediate rate of potassium, it seems like you had the most response to nitrogen, and at the highest potassium rate, you had still a response, but maybe not as strong. So just creating some visual understanding of our data. All right, so now we're going to get into our statistical model. So we brought in data, we wrangled, we did some exploratory data analysis with tables and plots. Now let's get to creating the model behind this data set here. So I left you here. This is a part of the code that we're going to work together. So if you are following along, you can start typing with me right here. It's going to be the only chunk that you're going to have to type. So because I want to do a randomized complete block design with blocks as random, we're going to use the function LMER from package LME4, which allows us to run mixed effect models that basically are when you have fixed and random effects in the same model. In our case, our fixed effect is going to be our treatments, our random effect is going to be the block. So that's why we're using this function. So if you come here, we can start typing. We're going to use the function LMER. I want to just, so the data set, let me just scroll up a little bit here. Data set we're using is this RCBD DFW. I just want to print that on this chunk so we see what columns we have available to create this model. So yield, kilograms per hectare, is our response variable. So we type yield, we give it a tilde to say yield explained by, and then we give our fixed effect terms of this model, which is basically going to be N rate. We use an asterisk and potassium rate. So this notation of one factor, asterisk, another factor, basically breaks this down into the main effects. So nitrogen rate main effect, potassium rate main effect, and the interaction between two. This is what the asterisk in R does for us. And this is the fixed effect part of our treatment, is what we want to know about the means. I want to know the mean yield for each level or each treatment combination between a level of nitrogen and a level of potassium. Now, I did tell you that we want to run our blocks as random. So to do that, we add a plus here. I want to hit return just to break the line and make it easier to see. But we want to say the way that we determine that block is random is to open and close parentheses, type in a 1, type in a vertical bar, and just specifying the name of the column that has the block information, which is rep. So this is how we would tell the function that we have our fixed effects, which is this part here, and rate, asterisk, potassium rate, and the random effect, which is blocks treated as random. That's how we specify it. We also give it a comma, and we want to say what is the data, where is the data that we're going to be using here. So the name of the data set is RCBD DFW. So if you just say data equals RCBD DFW, that should work. Now, I'm going to run this first line here, options, to change the contrast from set to 0 to sum to 0. We don't have enough time to talk about that, but I'm just changing that default, running my model, which is going to be run and saved into this object RCBD mix mod. If I just print here RCBD mix mod, we see it's a linear mixed model. We have our random effects here of rep, and then we have our fixed effects here. So this output here normally is not the one that we look into when we run analysis of variance. We want to look into the ANOVA table, which is going to be the next chunk here. So we're going to use this function uppercase ANOVA so we can get a type 3 sum of the squares ANOVA. I'm not going to have a lot of time to tell much about that, but if you want to learn more about that, I have you can follow my class material. But we're running an analysis of variance table, which should be familiar to us, right? So we have here our source of variation, so nitrogen rate, potassium rates, and their interaction. Rep is not here because rep is not a fixed effect. It's a random effect, and ANOVA tables only show you the fixed effect part of the design. So I guess just to come back here and tell you, come back to our model. So this component here in this model is what is specifying the treatment design. This part here in this model is what is specifying our experimental design. So our experimental design of using blocks and treating them as random effects is being represented in this model by this term. All right, so if you come back to our ANOVA table, we always start looking from the bottom up, right? So we look first at the interaction. The interaction is highly non-significant. However, the main effect of potassium and the main effect of nitrogen are highly significant. So we would like to further extract those means and do pairwise comparisons for the main effects only. And that's what we're going to do. However, before we do that, we have to check model assumptions. So we can really only use this model for inference to make pairwise comparisons and understand the effect of those means after we make sure that the model is fulfilling the assumptions of the linear model. The assumptions of the linear model are all based on the residuals. So first we have to extract the residuals of our model and data, and then use those residuals to check the assumptions. On this next model here, in this next chunk of model, I am getting the residuals using this augment function. And then I am creating the studentized residuals as well, which are going to help us to identify outliers. So if you just go ahead and run this chunk, you're going to see here that we still have 36 rows. Now we have more columns. So we still have yield, the treatment effects of, or the treatment factors of nitrogen, potassium, the block effects. Then we have these extra columns here. So we have a fitted column, resid, hat, Cook's distance, fixed, and then all the way to the end, we have the studentized residuals. We're going to use these information here to check the model assumptions. Now, to just recap here the model assumptions, again, this is another full lecture, but we're just browsing very quickly here. But the assumptions we're looking for here is first independence. So we want our residuals to not show a pattern. We want them to just be a cloud of points that have no pattern in them. And that helps us to fulfill the assumption of independence. We want them to have variance homogeneity, meaning again, we want them to be just a spread of points. If we see like a funnel shape, which is kind of like this, it's not going to see on this data set, but sometimes you see this funnel shape. That means that you don't have variance homogeneity. You should fix that first on your model before you use the model for inference. We're not going to talk about that. This data set here has variance homogeneity assumption checked, as we're going to see in a second, but I just wanted to point that out. Also, our residuals should be normally distributed. Not the raw data, the residuals. And then also do outlier detection to see if we have any residuals that are below -3 or above 3 on a scale of studentized residuals. So these are the assumptions we're going to be checking, and I want to show you how to do that next. So because this model is a mixed effect model that has a random effect, that is the blocks treated as random, we also have to check for an assumption on the block effect. So I'm showing you here the code of how to extract that information, and then we're going to use what is called a quantile plot or QQ plot to check that assumption. If you just go ahead and run the chunk, this is basically what we're looking on a quantile plot, where the black line here is the line where if your residuals are normal, they should be really close to that black line. And then the points are the actual residuals, in this case, for the blocks. We see that one of the blocks seems to be kind of far away from the line. I wouldn't worry too much because we only have 4 points anyways. That's not really a lot of data to get a good understanding of the normal distribution. So even though this point here on the left is a little bit lower than I would wish, still is not terribly far away, and we only have 4 points anyways. So I wouldn't worry about this as far as the normality of the residuals of the random effects, or of the assumptions based on the random effects of blocks. All right, so now we're going to check our residuals coming from all observations. So if you just go ahead and run this plot here, this chunk here, It's going to produce a plot that we have the fitted values on the x-axis and the studentized residuals on the y-axis. I'm leaving here the red horizontal lines are at 3 and -3 on the studentized residual scale. What we want to see on this plot is a random spread of points. I'm also adding here a geom smooth, which just adds a regression line here represented by this blue line. What we want to see in this plot is that this blue line to be very close or touching the 0 intercept on the y-axis, meaning that there is no pattern in these residuals. They look like a random spread of points. I don't see a clear pattern. I don't see this funnel shape where the residual is very short on the left and very large on the right side of the plot. So this is what we would like to see. This plot here is basically showing us independence because I don't see a pattern, and I can make an inference around that, or not inference, but make an observation around that because the smooth line is touching 0 across the extent of the 0 on the y-axis. Also, I don't have any outliers because I don't have any points that are going beyond 3 or below -3. So no outliers, no patterns. The variance is homogeneous. I don't see that fan shape that we can see sometimes. So all these assumptions are being checked here. And then to check for residual normality, there are a couple plots we can use. This is again the quantile plot or QQ plot, where we want the points, the residuals here, which are the points, to be very close to this black line, and they are. So I'm not worried about normality here. We can also assess normality on this next chunk here using a density plot, where we want the mean to be 0 and to be within -3 and 3. And we see that the distribution of our residuals, they seem pretty normal. So really, these are the plots that I use to check for the model assumptions. It was check, 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 right? So everything is checking here. Residuals are independent. The variance is homogeneous. There's no outliers, and residuals are also normal. So at this point here, I would say this model here is a good representation of our data. All the assumptions were checked. The model is good. We can proceed with inference. So now the first thing on inference is going to be for us to extract the means. If you remember, the two main effects of potassium and nitrogen separately were significant, but not the interaction. Because of that, we're not going to be extracting interaction terms. We're just going to be extracting the main effects of nitrogen and then potassium separately. And this again is based on the ANOVA table that we saw on the chunk above on the script here. So for us to extract the means of nitrogen first, I'm using this function called EMeans, and I'm just given the model object and the term that I want to extract the means of, which in this case is going to be nitrogen. So if we just run this is going to print below those means. So we have the nitrogen rates, we have the EMean, which is the expected marginal mean of that treatment effect, and we see the mean yield for each one of the nitrogen rates. So we see that 0 was the lowest and 200 was the highest, as we kind of expected based on our EDA plots that we did in the beginning. All right, so in the next chunk, we're going to extract the means as well for potassium, but just potassium itself, not mixing potassium and nitrogen. So if we just go ahead and run this chunk, it's the same as before, but now we're asking for potassium to be the treatment factor. So again, we have the 3 means of potassium, and then we have the 3 levels of potassium and the means for those levels. All right, so we extracted the means. Now the next step is going to be to ask for pairwise comparisons. First, I want to do that for nitrogen. We're going to be using this function called CLD. And I just have some different things here going on that I'm not going to walk you through. You can check on this later on your own. But basically, if you run this chunk here, and we're going to print this output here, we have this data set now that has the nitrogen rate, the EM mean, so the mean coming from the model. And then if you scroll here to the right, you're going to see the letter. So these are the letter separation for those means. So we see that the highest yield was from 200 kilos of nitrogen per hectare, followed by 100, followed by 0, and the letters would be A, and B for those treatment factors, or treatment levels, sorry. We do the same thing for potassium. So if you just run this, it's going to be the same thing, but now apply for the potassium, where we have the rates of potassium, the means, and then at the end, we have the letters A, and B as well. All right, so at this point, we basically are ready to make our publication-ready plots. So if we come to the next chunk here, we're going to do that first for nitrogen. And I want to tell you something that I try to do, always try to do this whenever I'm working with my data, is I like to show raw data, so the distribution of the raw data, and the statistical summary, which in this case here would be the letter separation coming from a statistical model, together in the same plot. That way, your audience can have an understanding of the raw data distribution and also the statistical interpretation that you're getting from a model alongside with the raw data distribution as well. So I like to combine those two components of raw data and a statistical derived summary in the same plots. That's what we're going to do here in this next chunk. Again, I'm not going to walk you through exactly each line of code here. I just want to invite you to go ahead and run this chunk. And what you're going to see is our nitrogen, and this again is the plot for nitrogen, right? So I have nitrogen rate on the x-axis, yield on the y-axis. I have my box plots. I have the points jittered a little bit within those box plots, and then I have the letters. So here we would say that the highest yield was observed when a nitrogen rate of 200 or 100 were applied, and the lowest was significantly different from the previous two was when we applied no nitrogen. So the control lowest yielded the lowest, and it was significantly different from the highest two rates. The next thing on this script here is going to be a chunk that does the exact same thing, but for potassium. So if you just go ahead and run this, it's going to have another plot where we have here, again, a box plot and the points showing our raw data and the letter separation from the model showing here that the rates of potassium of 30 and 60 were highest yielding and were significantly different from when we applied no potassium. So this is basically the end of this script here. I want to save it. And I just want to tell you a couple things very quickly. This workflow that you saw, so if you look here on the outline, the workflow included the setup where we load packages and bring in the data. We do exploratory data analysis. We do wrangling. We do some plots to explore our data set, run a model, check the ANOVA table, check model assumptions. Based on the, if model assumptions hold, if you fulfill all the assumptions, which we did in this example, you are okay to proceed with inference using this model. Looking at the ANOVA table, we saw which factors were significant. We then further got those factors and got their means in pairwise comparisons, and then made two separate publication-ready plots based on that. So this workflow, you're going to apply to any experimental analysis data workflow that you have. What you may need to change perhaps is the model, right? So maybe your model, if you're running maybe a one-way instead of a two-way factorial, your model is going to change. You may need to change the random effects, right? Maybe you don't have random effects because you don't have blocks. If you did a CRD, you don't have blocks. So the model chunk may be the one that you change. And then of course, the way that you extract means and do pairwise comparisons should always be based on your ANOVA table, which will change depending on the model and the data. But this overall workflow is pretty consolidated for this type of analysis. You just have to change things here and there, but the workflow remains very similar. So this is going to be a resource that you have. Again, the code is on GitHub. I want to share with you as well. So this was the code that you could actually come and change the code, right? You could come here and test the code, do different things. We didn't have enough time to do that in this workshop, but you still have this code available that you can edit it. However, if you were not able to follow along because of whatever reason, I also have a version of this code. So I went back to the GitHub repo. There is a rendered script version of this code on this link here. So this link is in the GitHub repo for this workshop, that if you click on there, you have this exact same code, but rendered. So it has a table of contents here on the right that you can navigate. It has all the code that we just saw. you're not going to be able to run it. It's already run for you, and it's just showing you the code, the output, and the comments, just like the script that we just developed. And you can use this as a reference as well. So this has all the same plots, all the same code, tables, data, everything as what we just saw. You can use this as a reference as well if you don't want to. This you can look into your browser. You don't have to have R to really even see this file here that I'm showing you. Of course, if you were coding along and following the code, you would have to do that in R with this script here. All right, so very quick summary here. We saw on the lecture some of the concepts of study design, which include treatment and experimental design. We saw this example here of using a 3 nitrogen by 3 potassium factorial as our treatment design, and using a randomized complete block design with blocks treated as random as our experimental design. Then we came here on the script and we implemented that analysis where we brought in data, explored the data first, did some wrangling, ran a model, checked the model assumptions, extracted means, did pairwise comparisons, and then finally produce a publication-ready plot. So this is the workflow and the workshop content I had to share with you. I think we may take a quick moment here if anyone has any questions or if you have any thoughts, and then we can go from there. So anyone has any thoughts or questions here?
So, Dr. Bastos?
Yes.
Yeah. So I'm wondering, say, in your case, nitrogen and potassium rate, their interaction was not significant. But if they are significant, is it possible to plot their combined effect and have, like, how do you display that? Is it the scope of this presentation, or it will take longer? I can chat you later.
Yeah, so we didn't cover that here, but it would be very easily done. So just to quickly demonstrate here, let me minimize. So Abdullah was asking if the interaction was significant, how would we treat that? So what we would do, so I'm looking here on my outline, it would change basically on model means, right? So if I come on model means, where we did separately for nitrogen and potassium, here, instead of doing just like tilde nitrogen, I could do tilde nitrogen and then colon K rate, kg hectare. So if I ran that, so just adding this notation here, it would give me the interaction. So it would give me nitrogen, potassium, and then when I run then the CLD, the pairwise comparison function, it would give me the ladder separation for all these levels here. So it's very easy. You could get the letters that way. And then when you're making the plot, of course, you have to adjust things to bring in both nitrogen and potassium on the same plot. And I'm not going to have time to show you how to do that at this time.
No, but yeah, thank you. I get it. Yeah, absolutely.
Yeah.
Brilliant. Thank you.
But this is how we would do that. Yep. Yeah, thanks for the question. All right. Any other questions or thoughts? If you wish to ask a question in the chat, you're welcome to do that as well. All right. Well, I don't think we have any questions, and we're already 15 minutes past time. So I guess from my side, I just want to say again, thank you for the invitation. Again, this was a lot of content in a very short time. If this was the first time you're learning about experimental design, if it was the first time you're learning about R, it was completely overwhelming. But I hope that for those of you that had some experimental design knowledge and had some R knowledge, that this was useful for you to be equipped to have a workflow that you can follow, adapt to your studies, and be able to conduct this type of analysis with a starting point. And again, I have more resources from my classes that are all available online that you can use to learn. If you have questions or issues, I'm always open to helping out as well. Just reach out. And I think that was it. So from my side, thank you very much. Thanks again, Jessica and Amrinder, for the invitation.
Thank you, Dr. Bas. It was a really good presentation. I really enjoy it. And I think you help everyone here a lot. Most of us are working with that. So thank you. You're going to post in your website, right? This recording?
Yeah, so the recording, I'm gonna post to my YouTube channel, and then I'm gonna put a link of that on the GitHub repo where I have the links for the slides and the render script. I'm also gonna have a link for the presentation as well. And I'll share that link with you as well, so you can share with the group by email.
Thank you. Thank you so much. Yeah, I appreciate it.
Absolutely. Thanks for the invitation. Thanks, everyone. All right, I'm gonna stop recording here. Stop sharing. Thanks, everyone.